Any questions on the homework? Let's get started with the class today.
The last part of 5.
Yeah. So again, this is exactly similar to what we have done for the BCD adder. Okay, exactly the same way. The only difference is you're adapting the same approach for a tertiary adder. That's the only difference for a tertiary full adder. So you would apply the same principles to solve that. Of course, you can do the longer way, but that but that's not something I would recommend. You would like to go with the the modular approach and a more, what would I say, elegant way, right? Okay, so I do have a recording that details the solution for that, so I'm going to post that later on. But I hope but I would again want you to rewatch the BCD adder lecture if possible, and see if you can actually do it yourself. Because if you can get it, that's actually very you'll feel happy about it, because that's I think that was a very interesting problem. Okay, so let's move on. So in today's class, we're gonna so in the last 2 classes we talked about adders and subtractors. We also looked at the modular approach, right? And now we're going to talk about slightly different way of doing things. Okay. What happened here? Okay, so let's do that. So in today's class, so we're going to do what is called the conditional testing. What is it all about? So let's actually introduce this topic. Let's get started with asking few questions about it, and then let's try to see if we can answer those questions through this course, through the course of this lecture. Okay, so let's ask this question to ourselves. Number 1 is, most of you at some point in time must have done some kind of programming, right? You must have done some kind of programming, and of course at a much higher level. So what is really what we are trying to do really, right? As a programmer, you're trying to see if you can actually make the computer do some routine activity, right? So that's exactly what you're trying to do. Okay, now we want to automate some routine activities. Of course, when you're trying to program, the brain is still you. As a programmer, you're still the brain behind everything, right? You're using the computer more as a help to do some routine activity, the routine operation. Okay? Now, having said that, of course, things are changing now, right? Because now as things are evolving in terms of the computational efficiencies of the systems, we are able to do machine learning and artificial intelligence. Of course, we are able to give some intelligence to the machines as well, but traditionally this was not the case, right? Basically, the programmer is the person behind the brain, and of course we are using the computer more as a help. Okay. All right. So we still have the computer. We still look at the computer as still a passive device without its own intelligence. The intelligence is you as a programmer. Now, when you want to make something programmable, right? You want to ensure that it's able to take some decisions. Of course, the decisions you program it in such a way that you're enabling your computer to take some decisions for you, right? Let me put it that way. So how is it being able to do that? Now, because this course we are actually targeting the hardware, right? A good idea moving on is to see how the program, when you write a program at the high level, which you're familiar with, you don't have to be experts on that, but at least if you have some basic knowledge of some program, you're writing the program at the high level. When I say, again, you can classify the program itself into what is called the high level language that you must be more familiar with, and then you can go the hierarchical way. Then you have what is called the assembly language. Okay, that's one step closer to what's exactly happening at the hardware level. And then you have the machine code, which is basically your ones and zeros. Because again, if you think about it, your computer is basically a device that can only understand zeros and ones at this time. It cannot understand anything else, right? So whatever you put down in there inside the device has to be in terms of zeros and ones. Whether it's data that you're working with, whether it's programs you're working with, everything is in terms of zeros and ones. Okay? So even your program, so each instruction is encoded as a 0 and 1. Okay? So that's the idea behind this. All right. So so now when you write the high level language program, how is it being manifested at the low level, basically in the machine code, at the computer level, at ones and zeros, right? How is the hardware able to take some decisions which enables the programmability aspect to your program? Okay, I'm hearing an echo from there. Can you please want to make sure that your microphones are off unless you want to speak something? Okay. All right. Of course, you mentioned compiler, but at the hardware level, let's examine in a little bit more detail what's happening. Now, let's take an example of the code. Like when you're writing a program, again, you want the computer to perform some routine operations. So, how would you do that? Right? Let's take an example of a code. For example, let's say, at high level, you can use the examples of or the aid of these if-else statements. That's one way of doing this. So, for example, if one way of doing some routine, letting the computer do some routine operation would be starting with some code. Say, okay, if let's say a equals b, there are two variables, so you assign some value to those variables, and during the progression of the code, if a equals b, you ask the computer to do certain set of operations. Okay, and then else, again you're doing a conditional testing, right? If a equals to b, that means you're basically comparing those magnitudes together. And then if a larger than or equal to b, you ask the computer to do a separate set of instructions. Okay. And then of course, if you can write this. If a less than b, again a separate set of instructions, and so on. So basically, you're asking you're enabling the computer through the program to take some decisions for you based on these instructions. Okay. So you're basically doing the conditional testing. Okay. Other examples, of course, other examples of high-level language code would include a for loop. For example, you can actually ask the computer to do some operations based on a for loop for I equals, let's say, from variable I equals 1 to n. You ask the computer to do some particular operations, and then you increment I, and then every time it basically once every time the loop is executed, it goes back, checks for I. If the condition is not satisfied, it runs through the same program, same instruction, right? And then of course your other example is a while loop. So all of these enables you as a programmer enables you as a programmer to perform some operations by the computer, right? In an automatic fashion, in a programmable manner. Okay, I will do that. Okay, so let's start with that. So how are we able to do this at the hardware level? Just as when we discuss the construction of adder, let me actually turn on these lights. That will make it more clear. Okay. When we discuss the concept of adder / subtractor, right? Now, when you're writing the code, if I want to add, right, yeah, you basically do a plus b, and then at the hardware level, we discussed that you need to have some kind of a control input that would place a 0 on the control input to add, a 1 on the control input to subtract. Right? So when you write a code at the high level as a minus b, what is happening at the hardware level is you're basically applying a control input of 1 on the control, and then basically your hardware is reconfigured as a subtractor, or your adder is reconfigured as a subtractor, and then you're doing the subtraction operation. Right. So every time, so moving forward, what you should think about is what I'm doing at the code level, how is it translating at the hardware level, at the very low level. Okay. So it's a good idea to connect those two pieces. So far you haven't done that, or at least you haven't done that. And moving forward, that's what I encourage you to do that. Okay, how the hardware gets affected by the code. All right. Now you see the shared screen document over there. I just wanted to illustrate some interesting aspects there. Okay. You see that? Yes? Okay. So what I have here is an instruction set. Again, as I mentioned before, you can classify a programming language into three, broadly classified as into three programming languages, if you will. Okay. So one would be the high level language that you're familiar with, that more or less looks like your regular English. The second one, you're going down one level, is the assembly language, okay, where you work with mnemonics. Okay. Now, if you want to work with assembly language, you need to know the hardware configuration. For a high level language, you don't really care about what's happening with the hardware, or the hardware is, you don't know, you have to care about the architecture of the hardware. But when you're working with an assembly language, you work with mnemonics, short codes, okay, and you're basically one level ahead than the machine code, which is basically ones and zeros. You're basically right there near the hardware. You're working really at the interface of the hardware, if you will, when you're working with assembly. Now, what's the advantage of using assembly? When you write programs at the high level, you have a lot of redundant code that goes on into the program, into the program memory. Now, on the other hand, when you're working with assembly language, your programs are more compact and more efficient. Because it's more compact, the instructions take more, they are run more efficiently, and that saves space on your hardware. Especially these are typically done. The assembly language codes are typically used for programming embedded systems, because again, that's a small system, you want to be as compact as possible. Now, again, the idea is you use the mnemonics, and each mnemonic is associated with a code, with a binary code. Of course, as you can see in this table. All right. Now, pointer. Do you see the pointer? You see the pointer, right? So you can see that. So that's the mnemonic. Right here, you have a CMPA, okay, which basically stands for compare a value in a temporary location with what is stored in a memory location. Just as an example, compare CMPA with some number. Now, again, let's not worry about addressing modes here, but for each instruction, as you can see here in this table, you have a machine code. So when you enter this instruction in your compiler, what's written in the memory, in the program memory of your device, is this machine code. So in this case, you have for this particular instruction, it says it is basically 8-1. Again, this is written in hexadecimal. Remember that the hexadecimal representation is a more compact representation of binary representation. Right? So instead of working with ones and zeros here, it's basically represented in the hexadecimal form. 8-1. So 8 is 1000, and 1 is 0001. So that's the code for this particular instruction, CMPA. And of course, you have II that basically refers to the address, because the address can be anything, right? Each memory location will have an address, and that's where you put down information, again, as a binary number. Your addresses are also binary numbers. So everything is binary. Ultimately, when it's stored in the device, your program code is binary, your addresses of the memory locations are binary, everything is binary, right? So that's what you have there. Just as I just wanted to basically give you taste of what really happens when you're working with assembly language code, what's happening at the hardware level, and how everything is interrelated. All right. Now, let's. So with that, again, I wanted to show the instruction, the compare A, right? So it's very similar to, like for example, when I'm trying to do this when I'm trying to do this conditional testing, right, I have if A equals B, sorry, was there a question? All right. If A equals to B, do some operations. So at the hardware level, I can write the same instruction as compare A and B as an assembly language code. All right. At the high level, the code looks like something like this. At the hardware, when I'm writing it as an assembly language code, my instruction looks like compare A comma B. Now, at the hardware level, what is happening there? When I'm doing this operation, as you can see here, as you can see here, what the operation that is being performed is A minus B. Okay? In this case, of course, A minus whatever is stored in the memory location. But here, for this particular instruction, what I'm doing is A minus B operation. That means I'm using my subtractor, my array slash subtractor, as a subtractor, and I'm performing this A minus B operation and testing for the result. Okay, and then testing for the result. How do I test it for the result? I'm not really interested in the magnitudes of A and B. What I'm really interested in is A minus B operation. Okay. Now, again, A minus B can be 0, and in this case, A is equal to B. A minus B can be larger than 0, in which case A is larger than B. A minus B can be negative, in which case A is less than B. Right? So all of those conditions may happen. Okay. So how do I test the result? What I'm doing here at the hardware level is we do that through the implementation of flags. This is an important concept. So what enables you to perform the conditional testing is the flag. So let's actually define what a flag is. So in today's lecture, we'll talk about flags. A flag is basically a 1-bit indicator, if you will. You know, we use the term flags all the time, right? In language, in colloquial language, we say something that raise the flag. So basically, it's an indicator for something. Okay. Now, what kind of an indicator is it? For example, I can basically produce a flag. I can basically produce a flag to indicate the result of an operation. I'll give you an example here. Let's take some examples that will make things more clear. For example, if I want to test if A equal to B, I want to test condition. How do I test this? I can basically, of course, the first operation I need to do is A minus B. Right? That's the first step. I can use my subtractor, I can use my array slash subtractor, configure that as a subtractor, perform this operation, A minus B operation, and then I would test if A minus B equal to 0. Right? If A minus B equal to 0, that indicates that A is equal to 0. But how do I test if a minus b equals 0? I create a flag called a 0 flag. Okay. Now I will perform a minus b operation, and then I get some answer, right? Whatever the answer is, from that answer, I want to basically produce a 1-bit indicator called the 0 flag that will be set, so v equals 1, that will be set if, I will configure it this way, if a is equal to b, or alternatively if a minus b results in a 0, and z is not set, z is 0, if a is not equal to b. That's how I define my 0 flag. Okay. Now, how do I configure a 0 flag? Any suggestions on that? At the hardware level, how do I configure a 0 flag? Now, the hint is already in the operation, right? This is a statement. If I'm trying to check for this particular condition, the way I'm doing this condition is I perform a minus b operation. Okay, that means when I do that operation, I will get some answer. Then I'm testing for the answer if it's all zero, because if the answer is all zeros, then I should set my 0 flag. So basically, again, remember that these flags are 1-bit indicator. These flags are 1-bit indicator. Well, let's again. So Zach, I see your comment. Let's again, because we are trying to do this, we're trying to make this decision within the arithmetic logic unit. Okay, let's not go into memory at this time. Okay, so of course we talk about memory even within the ALU, the arithmetic logic unit. We still have these temporary memory locations we call registers, and these flags can be part of those registers. All right. So the suggestion was assign an address to an empty memory point, and then test to see if the space is filled after the operation. Yes, again, the space will be filled. Even if the operation results in a 0, actually zeros and ones are, they have symmetry there, right? Zeros and ones are equally important here. Even if the answer is 0, it will be filled with 0. Yes. So I would still need some way to detect if the answer is all zeros. That means if I would have to come up with an output, okay, for which if the answer is all zeros, the output should indicate a 1. If the answer is not 0, then the output should be a 0. Okay? And that's how I define the 0. That's how I define the 0 flag. Now let's start. In order to do this, let's actually start with we go back to our adder/subtractor circuit. Let's start with that. All right? And then we'll go from there. So your adder/subtractor circuit would look something like this. Right? So let's say I'm doing an 8-bit adder slash subtractor, 8-bit adder slash subtractor, and you know the construction of this, right? So basically what we have is your A's are going in. Again, this is another compact way of representing multiple lines going into a device. In this case, instead of actually showing 8 lines, I would basically show this as A and 0 to 7. That means with the slash, which shows that you actually have 8 lines going in. Right? And that's my C in for this adder, for this 8-bit adder. Then I have these going in through these XOR gates. That's my control. So I can basically, depending on what I apply on the control, I can configure this circuit to add or subtract. We know that already. So this is a adder slash subtraction circuit. Now I have, let me actually explicitly show all the outputs here. I have 8 outputs for the sum. S0, S1, S2. Again, when I say sum, it doesn't have to be sum all the time, right? The way I configured this, I configured this as a subtractor, then what I get this, what I get the sum is basically the subtraction to this, right? When I configure this as an adder, what I'm getting here is the addition operation, the result of the addition operation between A and B. And of course, I have to see out. See out. Right. Okay. Now, when I'm doing this operation, compare between A and B. Basically, what's happening at the hardware level is A minus B operation. Okay, and I'm testing if A minus B. Compare it if A minus B equal to 0. I'm basically doing this particular testing, and I want to construct a Z flag. Okay, that is equal to 1 if A is equal to B, equal to 0 otherwise. So now let me see if you can actually think about some way to construct a Z flag. The Z flag in this case is the output, right? Again, go back to your basics. That will help you design this circuit. The Z flag is the output. What are the inputs? So basically you want to design something. That's your level 0 design, where what this has to test if the applied inputs, in this case you're looking at the sum, right? 8 inputs here, S0, 1, so on, S4, S5, S6, S7. So you have 8 inputs, and that's your Z, we call that Z flag, that's your output, Z flag. Z flag should be 1 if all these inputs, S0 through S7, all of them are 0, equal to 0 otherwise. Does it make sense? So that's how I would construct my Z flag. Whatever the circuit that goes here would be how I obtain my Z flag. Okay? My flags are 1-bit indicator. So what should be going in here? Does it make sense, by the way? For conditional testing, if A equal to B, we're doing A minus B operation, and only when S0 through S7 are all zeros, then the Z flag should be set. That indicates that A is equal to B. Any suggestions on how should I implement this particular block? So I'm basically taking these values as inputs to a block, giving me an output of Z flag. That should be 1 if all of those individual inputs are taken. An OR gate, perfect. That's all I have to do. Right? Now, if I use a NOR gate, why NOR gate? Because if I look at the NOR gate truth table for the NOR gate, if I have A and B inputs, S is the output. These are all those different possibilities. Again, NOR is the inverted version of OR, right? For an OR gate, I have all of these are 1s except for 0, 0 condition. All of the rest are 1. For the NOR gate, for 0, 0 I have 1, and the rest of them are all 0. So a NOR gate would give you an output only when all the inputs to the NOR gate are 0. Right? Only then the NOR gate output is 1. So in other words, I can construct my Z flag by basically sending all of these inputs to a NOR gate. That's my NOR gate. and now I got my Z flag. It's a 1-bit indicator that tells me when A is equal to B. I'll perform A minus B. I can use my Z flag to test if A is equal to B. I hope that makes sense. Likewise, we can do a number of different operations, number of different conditional testing, right? This is one test, one conditional testing, A equal to B. I can also do, how about, let's actually work with signed numbers, unsigned numbers first, because unsigned numbers is more simpler to work with. So let's work with unsigned numbers conditional testing. Now that brings us to the next question. Let's say I'm trying to work with unsigned numbers. Now, the question is, I have this piece of hardware here that's within my arithmetic logic unit that forms the kind of the brain of your system. Now, how does it work? Because I may be working with signed numbers and unsigned numbers, right? Depending on what kind of data I'm working with, the data can come as signed data, also unsigned data. And the question that you should be asking is, this piece of hardware, do I need a different piece of hardware to perform signed operations and unsigned operations? Or can I use the same piece of hardware to perform both these type of operations? So that's the question that you need to be asking. What do you think? Do I need a separate set of hardware, like the adder subtractor, that can perform, that is kind of tied to signed operations, and a separate piece of hardware for unsigned operations? Or is it the same piece of hardware I can use for both signed and unsigned operations? So that's the first question. The second question is, okay, let me see what you think about that. Is it the same piece of hardware, or do we need two different pieces of hardware to perform signed operations and unsigned operations? What do you think? It's the same. Okay, very good. It's the same piece of hardware. Yes. The follow-up question to that would be, how does this piece of hardware? Because again, it's a hardware, right? It's only all it knows, all it can see is basically zeros and ones. So how can this piece of hardware, the same piece of hardware, distinguish between signed operations and unsigned operations? Right. And the answer to that question is the hardware doesn't do that. It is you as the programmer who does it. Okay. As far as the hardware is concerned, it only just reads the zeros and ones. There is no thinking or intelligence involved there. You are the programmer who will do that. How would you do that? Again, it brings back to the concept of flags. We use flags to distinguish between signed and unsigned information. Okay? All right. So let me see if I can. Yeah, let me actually do this. So let me actually cover the flags first, and then we'll examine how it is done. But at the back of your mind, you should just have the question: how it is able to do that? How it is able to distinguish between signed and unsigned operations? Okay. Now let's actually look at other possibilities here. We looked at the Z flag. That's one of the flags that can point to a particular operation, okay, particular condition. Now we'll also look at, again, I'm trying to compare A and B, and I can have all these possibilities, right? I can have A larger than B, A less than or equal to B, A equal to B. We have already done this. I can do this by using the Z flag. I can test if A equal to B by using the Z flag. Now, what about these operations? Again, let's assume for now, let's constrain ourselves to unsigned operations. So in this case, I'm assuming as a programmer, I'm assuming that A and B are unsigned. There was no sign associated with it. Now, what kind of flags will I be needing to be able to do those conditional testing for these subsequent conditions? A larger than B, A less than or equal to B, A larger than or equal to B. That's another condition I need to test. So why do I need to do this? So just to give you a flavor of, of of an assembly language code, let me actually do this so that may actually help bring things into perspective. So the way I write an assembly language code is this is how I do it. This is my memory where I'm storing my code. So I start with some memory location. Each memory location is again numbered, which have an address, a unique address associated with this memory location. So I store my code. So my code goes sequentially. I write my code. So each memory location will hold a machine code, the ones and zeros. Right? Whatever you type in the mnemonic gets converted into machine code by the compiler, and your memory would basically store that machine code. And each memory location will have its own unique address. Right? Now, when I'm trying to do some conditional testing, like for example, when you're trying to do some if-else statements in your code, a corresponding code in assembly would look something like this. So let me see. The corresponding code would be something like compare, let's say A and B, two variables A and B. Okay. Now, and then we use a code called branch, because we are working with these with memory addresses. Branch is equal, let's say, to, and I have specified a different address. So basically, you now, as the name suggests, the branch statement, you're executing the code sequentially, one after, going one location to the next, and then you encounter this conditional testing code here. Let's say compare A, comma B. Of course, in this case, you're doing this A minus B operation, and the next instruction is branch is equal to a different address. That means I'm looking at the Z flag, the status of the Z flag, and if the condition is satisfied, then I jump from this, let's say that is branch is equal instruction. Then instead of executing sequentially, I branch to a different address and then start executing the code from that address. That's similar to your if-else statement, right? Does it make sense? How this works in the assembly language? So you do the conditional testing. I use some instruction slug called branch instruction to break that sequence. Okay? So I go sequentially until this point. Then I do some conditional testing. If this condition is satisfied, and whatever address is specified here, I branch to that address and start executing the code from that address. And the process is continued. I hope that makes sense. Just to give you some flavor of the assembly language coding, how it works. Now, similar to branch statements, branch if equal, I can also have branch if higher than, or branch if lower than. Again, depending on the A and B, I can write similar branch statements for other condition testing. So when I say branch if higher than, that means if that is equivalent to saying if A is larger than B, then go to a different set of address and start executing the code. Likewise, if branch is lower than, that corresponding statement in higher language would be if A is less than B, then go to a different address and start executing the code. And so that's how your branch statement works based on the condition. Now at the hardware level, what is happening? I need to come up with different flags to test this condition as well, right? So now let's look at how do we configure those flags that can allow me to test if A is larger than B, A is larger than or equal to B, A is less than B, A is less than or equal to B, and so on. Now again, for now let's constrain ourselves to unsigned numbers. As a programmer, again, I'm trying to, I'm the one who's giving meaning to the data values. So in this case, I'm considering A and B as unsigned numbers. All right. Does that make sense? Any questions on this? Again, on an intuitive level, I'm just trying to see, trying to connect these dots. I'm hoping I'm able to connect those dots for you guys. Any questions on this? All right. So if you have no questions, let's move on to trying to find the flags, or trying to configure flags that can do A greater than B, A less than or equal to B, A greater than or equal to B. And of course, A strictly, so this is A strictly larger than B, A less than or equal to B, A larger than or equal to B, and then A strictly less than B. So these are the 4 conditions I want to test using flags. Okay, so how do we do this? Again, whenever I'm doing these conditions, the first operation I'm doing is A minus B. Of course, I've already done this. The first operation I'm doing is A minus B, and then based on the result, I can come up with my flag. Just like how we have done for A minus B operation. I'm looking at the answer. If the answer is all zeros, my V flag will be set. And likewise, I would like to come up with these conditions. So, any intuitive ideas on how do we do this? Based on the result, any ideas on how to come up with flags that can test those conditions? B minus A is greater than 0 for A is larger than B. Okay, so how do I test for that condition? Now let me give you a hint. When I'm doing this A minus B operation, because that's the first thing that is done, right? Whenever I write a compare A comma B operation, that is what is happening at the hardware level. And my hardware basically performs A minus B operation. How is it able to perform that operation? It's doing that by taking A plus 2's complement of B, right? Using this adder, configuring that as a 2's complement subtractor, and taking A, adding that to the 2's complement of B. Now when I'm doing this operation, based on the result, how do I know if A is larger than B or A is less than B? Going back to your 2's complement subtraction operation for unsigned numbers. How do you test? What happens when A is larger than B? When I do this operation, what is that indicator that can indicate that A is larger than B? Yeah, perfect. Carry. So I use my carry up, right? Remember that for unsigned operations, when A is larger than B, then A minus B, which is basically A plus 2's complement of B, gives you a carry out which you reject, right? Gives you a carry out, and you basically in the actual operation you basically ignore that carry and just look at the answer as being contained in these. Likewise, so obviously when A minus B is less than 0 or A is less than B, then you don't have the carry out. So I can use my carry out itself as a flag, right? That can indicate this condition or this conditional testing. That's not, of course, that's not the whole picture here. I still have to do something more, but at least we are getting there. So I can use carry out as part of my, I can use carry out to configure my flag that can indicate to these options. All right. Now, in an actual microcontroller, the way it is configured is when I do the, of course, right, the way this particular circuit is configured right now, when I say A minus B is larger than 0, implies my carry out is equal to 1. That indicates that A is larger than B. Now, in an actual controller like a like the one I just showed on the screen, that's the Motorola CS12. The way the C flag, the carry flag is set, is configured, is that when I'm doing this operation, if A minus B is larger than 0, then my C flag should be 0. Again, my carry flag is not the same as C flag here, and then A minus B is less than 0, then my C flag should be 1. This is how it's configured. So I need to do something else to the C out to be consistent here. That's all I'm saying. Now, how do I get this? Why am I doing this? The reason why it is being done is when I'm doing the subtraction operation, I would like to consider my C flag as a borrow flag, as an imaginary borrow flag. Just as an example, let's say my A is 3 and B is, let's say, 5. Of course, A is less than B here. Then if I want to subtract, perform this operation, obviously I cannot subtract 5 from 3. I have to borrow. In this case, I don't have a borrow. So what do? I borrow from an imaginary borrow. Right? Let's say, just think about that as an imaginary borrow. So every time I have to borrow from an imaginary borrow, then I will set my C flag to be a 1. So that's how I define my C flag in this way. That would indicate that whenever I have to borrow from an imaginary borrow, that means my A is less than B. When I don't have to borrow, then A is larger than B. That's how I define my C flag when I'm doing the subtraction operations. When I'm doing the addition operations, so let me just summarize here. So what I'm doing here is defining a C flag that operates this way, that functions this way. So I'm doing the subtractions. Okay. If A minus B is larger than 0, my C flag should be 0 because I don't have to borrow. If A minus B is less than 0, then my C flag should be set because I have to borrow from an imaginary borrow. My C flag should be set. That's how I'm defining my C flag. When I'm doing addition operations, if my circuit is configured as an adder, I use my C flag as an overflow flag. What do I mean by overflow? Again, remember that I'm working with unsigned numbers. Okay. When will I have an overflow? When let's say I'm trying to add two numbers together. All right, two unsigned numbers together. When will I have an overflow? What do I mean by overflow again? Overflow happens when my sum cannot be stored in those fixed number of bits. Let's say I'm working with 4-bit numbers. Okay. When I'm adding two 4-bit numbers, when the sum, the resultant sum cannot be stored in those 4 bits, I have an overflow. Right? So what would be a good way of testing for overflow in this case, for unsigned numbers? What would be a good way of testing for overflow? Any suggestions here? For example, let's say, for 4-bit numbers, when do I have an overflow? As long as the sum is less than 15, I would not have an overflow, right? Because for 4-bit numbers, for unsigned numbers, I can represent any sum between 0 and 15. The maximum sum would be 15. If my sum exceeds 15, let's say if I'm adding 7 to 9, all right, my sum is 16. 16 is larger than 15. Would I be able to represent 16 in 4 bits? I will not be able to represent 16 in 4 bits, right? I need another additional bit. How do I test for that overflow condition? Carry. I have, again, I can use the C out because let's say I'm adding 7 to 9. Again, both of these numbers are unsigned. So what is the answer? 1, 1, 1. 9 will be 1, right? 7 to 9, so 1 plus 1 is 0, 1, 1 plus 1 is 0, 1, 1 plus 1 is 0, 1, 1 plus 1 is 0. This is my C out, the output carry. C out is a 1. If I had an additional bit, then this would be the right sum, because that's 16, right? But I don't have that additional bit. This is basically C out. You can take another example. Let's say I'm trying to add 8 and 8 together. What do I get? 8 and 9 together, let's say. It will be 1, 0, 0. 1 plus 1 is 0, and I have a C out. This is the right sum, that is 17. But since I'm working with 4-bit numbers, that this sum exceeds my 4 bits. So I have an overflow. That's causing me an overflow condition. So how do I test for the overflow condition for unsigned numbers? I can basically set that. I can use my C out to indicate an overflow condition. Okay. All right. So when I'm doing the addition operation, right, then if my A plus B results in an overflow, or in other words, if my C out equal to 1 here, implies my C flag should also be a 1. So in this, when I'm doing the addition operation, I will use my C flag as the overflow indicator. As the overflow indicator. When I'm doing the subtraction operation, I use my C flag as the borrow indicator. Does it make sense? When I'm doing the addition operation, my C flag is the overflow indicator. Every time my C flag is 1, that means it indicates that I overflowed. My sum overflows the available number of bits. On the other hand, when I'm doing the subtraction operation, I want to use my C flag as the borrow indicator, the imaginary borrow indicator. All right. Let me pause here and let me see if you actually get this. Any questions on this? Unfortunately, I cannot see your faces here, so I really don't know if you're completely lost or are you with me until this point. What is the wording under adder? Okay, A plus B results in an overflow. When A plus B results in an overflow, my C out is 1, we have already seen that, and I would use my C flag to indicate the overflow condition. When my C out results in a 1, I would like my C flag to be a 1. That's how I would like to configure my C flag when I'm doing the addition operation. On the other hand, when I'm doing the subtraction operation, when my A minus B is larger than 0, then my C flag is 0, right? I would like to configure my C flag so that my C flag should be 0. And when my A minus B is less than 0, I would use my C flag to be a 1. So I'm basically using my C flag as a borrow indicator. Okay, very good. So let me write it down with respect to C out here. When my A minus B is larger than 0, if I'm looking directly at the C out here, C out, directly coming from the adder, you'll see that my C out is 1. But I want my C flag to be a 0 in this case. That's how I would like to configure my C flag. When my A minus B is less than 0, the C out that is directly coming from this adder, my C out directly coming from my adder is 0, but I want my C flag to be a 1 under these circumstances. When I'm doing the subtraction, when I'm doing the addition operation, when my A plus B results in an overflow, my C out is 1. I would like my C flag to be also 1. Okay? All right. Now, with that information, would you be able to tell me how to configure my C flag so that when I'm doing when my circuit is configured as a subtractor, my C flag is basically the inverted version of Cout. When my circuit is configured as an adder, my C flag is the same as Cout. Any ideas on how to be configure my C flag? Yes. So C flag is not Cout is subtraction, and C flag equal to Cout is adder. That's exactly right. How do I configure that now? Can I do something so that it's consistent, so that I would obtain that operation? Let's see. How do I determine if in subtraction or addition mode? Yeah, that's something you should tell me. How do I determine that? By the control, right? Exactly right. Because my control determines if my adder is configured as an adder or a subtractor, right? So now, just like the trick we have used here, because based on the control, I can either invert B or not invert B, right? Because if I apply control of 0, my B's are not inverted. This particular circuit is configured as an adder circuit, and I perform this operation as an adder. If my control is 1 here, I would configure this circuit as a subtractor. My B's are inverted, adding 1 to that B here, and I get the subtraction operation here. Right? So similarly, the trick I can reuse the trick here in this case. Instead of, so I can define my C flag. I can configure my C flag from the Cout using an XOR gate. So hooray, you're right. That's exactly how we should do that. I will use an XOR gate here. XOR gate between what and what? That's my XOR gate. And I will call this the C flag. So when this circuit is configured as an adder, then the C flag should be the same as Cout. When this circuit is configured as a subtractor, then my C flag should be the inverted version of Cout. And of course, because it is a control that configures this as an adder or subtractor, exactly right. I use the control here. The same control that's here. I use this control, and that's it. I got my C flag. So now I have 2 flags, and now I would like to see if I can actually get to these conditional testing. All right. So that's good. So how do we do this? So let's summarize this again. If my C flag equals 1, that means I'm borrowing from an imaginary borrow. Again, remember that I'm doing the A minus B operation first, and then looking at my C flag. My C flag is 1, implies A is less than B. If C flag is 0, implies A is larger than B. Okay. This is what we have done so far. All right. Now let's look at all of these conditions. I will do that with the aid of a truth table again. The aid of a truth table. Let me do that. Okay. So I have C flag as one of the input, V flag as the other flag. I'm doing the A minus B operation. Okay. And let's look at our possibilities between C flag and Z flag. So 0, 0 is one possibility. 0, 1 is another possibility, depending on the operation. 1, 0, 1, 1. Okay. So I'm doing A minus B operation, and then I'm looking at the flags, at the values of the flags. My C flag and my Z flag. Now, if my C flag is 0 and my Z flag is 0, what can you say about the A minus B operation? This is the operation, right? Okay, result of, let me put this as the result of operation. What does that indicate? If my C flag is 0 and my Z flag is 0. If my Z flag is 0, that means A is not equal to B, right? Because if Z is 1, then of course A is equal to B. In this case, I have Z flag as 0, that means A is not equal to B. C flag is 0, that means because I'm doing a subtraction operation, C flag is 0, that means I'm not borrowing from an imaginary borrow. So what can you say about the relative magnitude of A and B, between A and B? A is larger than B, correct? In this case, A is larger than B. Alright, for the second case, my C flag is 0, that means I'm not borrowing anything, but my Z flag is 1. What can you say about the relative magnitude between A and B? My Z flag is set, that indicates that A is equal to B, because my Z flag is only set when A is equal to B, right? In which case A minus B would result in a 0, and going through this NOR gate, that would set my Z flag. In this case, my A is equal to B. Alright, my C flag is 1 and Z flag is 0. What can you say about the relative magnitudes between A and B? C flag is 1, that means again since I'm doing the subtraction operation, my C flag 1 indicates that I'm borrowing from an imaginary borrow, right? So that indicates A is less than B. My Z flag is 0, that means A is not equal to B, so A is less than B. Alright, what about my C flag is 1 and my Z flag is also 1? This is a condition I would like you to test. Can this happen at all? For now, let me put it as A equal to B, but you'll see that normally doesn't happen. Okay. For now, let's just put it as A equal to B. But I would like you to test if there are any instances when both my C flag and Z flag are 1, and you'll see that you'll not be able to find that. Okay, from this truth table, now I will be able to derive the conditional testing for A strictly larger than B. Let's actually start with that first case. As the first case, what kind of condition, what kind of combination between C flag and Z flag should I test to ensure that my A is strictly larger than B? If my A has to be strictly larger than B, I need to ensure that my C flag and Z flag are both zeros, right? Does it make sense? If I have to test for A to be strictly larger than B, my C flag and Z flag has to be 0. So in what way can I arrange them so that that is satisfied? In this case, that will be C flag for A to be strictly larger than B, my C flag and Z flag should be a 0. Just examine this expression and see that makes sense. Okay. Now, if this particular condition is satisfied, I am saying that A is strictly larger than B. Does that make sense? As you will see here, if this condition has to be satisfied, then my Z flag can never be 1, right? Because if C flag is 1, then of course this condition is not satisfied anymore. C flag is of course 0. It has to be 0. My Z flag has to be 0, but this condition has to be satisfied. So for A to be strictly larger than B, my C flag, all I have to do is I check this condition, C flag plus Z flag should be 0. If the condition is satisfied, then A is strictly larger than B. Alright, so that's good. What about this condition, A larger than or equal to B? What condition should I test for to ensure that that particular condition is satisfied? Right. In this case, because I am no longer constrained to have my C flag to be a 1, I can simply say if my C flag, as long as my C flag is 0, then A is larger than or equal to B. Right? Does it make sense? If C flag is 0, because again I'm not placing any constraint, any condition on Z flag. Z flag can be a 1, in which case A equal to B. If Z flag is 0 and C flag is equal to 0, then A is larger than B. So either case it is satisfied. So for A larger than or equal to B, I test for C flag to be 0. Alright. So for the third condition, for A to be strictly less than B, A to be strictly less than B. Any ideas on what we should do? You see that this does not happen. So let me just put this as X. For A to be strictly less than B, then my C flag should be a 1. Because if my C flag is 1, then Z flag also 1 is not will not happen. And finally, the fourth condition for A less than or equal to B, again either my C flag should be a 1 or my Z flag can be a 1. So I can test for this particular condition to test if A is less than or equal to B. So in this particular condition is satisfied if C flag is a 1 or Z flag is a 1. Either case, this particular condition is satisfied. If to be strictly less than B, my C flag should be a 1. I am not placing any constraint on Z because Z cannot be 1 anyway. When my C flag is 1, then Z cannot be a 1. Okay. So now I have all the conditions. I have tested for all the conditions. A larger than B, A larger than or equal to B, A less than B, A less than or equal to B. All right. Any questions on this? On the flags. So now with this particular circuit, okay, yeah, we have already built the C flag and Z flag. So with this particular circuit, I would be able to test for conditions when I'm working with unsigned numbers. All right. Now, can I use the same flags for signed number testing? Just as an intuitive idea. Think about it. Let me know. If I'm trying to test, because now I'm done with the analysis of unsigned numbers. Now let's move on to the signed number testing. And by the way, for your next assignment, you will be required to actually simulate this circuit. So this is going to be different from all the other assignments where you have to just do your assignment to submit it. But this is going to be where you will actually use some kind of a simulation language. For example, B2Spice would be one of that, and simulate it. Simulate this circuit. B2Spice is just a suggestion, but you can also use NI multisim that can also do this. NI multisim, because you are only working with one assignment for one assignment, you should be able to download that like a trial version of that for 30 days. That will be more than enough time for you to actually work on this assignment. Yes, that will be, I have, so when I upload the assignment, the next assignment, you'll have the format for that assignment. You'll be preparing that assignment as a report, as a lab report. And you'll have screenshots of your simulation and so on. So again, it's going to be a very fun simulation because now you're actually working with the heart of the system, or the brain of your computing system, right? The ALU that can perform not only simple additions and subtractions, but can also do some decision making in the hardware level, right? By doing this conditional testing, you'll also be able to do some decision making that eventually enables programmability to your device. So you're actually one step ahead now. Just instead of just doing some simple arithmetic, now you are able to actually enabling the hardware to perform some decision making and automating some steps in the program. Okay. All right. So that's about the unsigned number testing, conditional testing. I hope that makes sense. For signed number, it's going to be a little bit more involved, not as simple as unsigned. But it's if you get the concept at the intuitive level, you should be able to understand it without any problem. So let me pause and take any questions you may have. Any questions? In the next class, if you don't have any questions, in the next class, let's see. The C out need to be 2-bit. Okay. So this question is about the last homework. My C out should always be 1 bit, no matter what number system you're doing. Just like we have seen for the decimal 2, right? The C out is always 1 bit. And you will see, as long as my two numbers, let's say if I'm doing a decimal operation, okay, I'm adding two decimal digits together, my carry out is going to be a 0 or a 1 always, cannot be more than 1. The largest two decimal numbers I can add, two decimal digits I can add is 9 plus 9, right, and maybe plus 1. So 9 plus 9 is 10, plus 1 is 11, my C out is still 1. So when I'm adding two digits of any number system, your C out will always be a 1 or a 0. I hope that makes sense. And that is that is in reference to the tertiary adder. Okay. Any other questions, guys?